Hello, this is the first video for the third week of courses. The first topic we're going to be covering this week is the last Laplace transforms. We're still going to be looking at a couple of functions and a couple of properties that Laplace transform has. So we have first, last week, looked into the delta function, and we have said that the delta function is in some ways the formal derivative of the Heaviside function. So let's look at the Laplace transform of the Heaviside function. The Heaviside function is marked by either capital H, calligraphic H, or in your book as U. So all this notation will be used at different times. It's always the Heaviside function. To distinguish it for normal use, I will usually point out when it is a Heaviside function. So let's look at the Laplace transform of the Heaviside function. Remember that the Heaviside function, it's 0, the Heaviside function of t minus a, it's 0 up to a and 1 from a onwards. So if we take the Laplace transform of it, we're taking an integral going from 0 to infinity, and the first thing we can do is just forget about everywhere the product inside the integral is equal to 0. So we can just start the integral at a plus, where I'm defining a plus as the maximum between 0 and a. This is just a trick to get rid of the part in which the Heaviside function is 0 and just not look at it. Now I have just the integral of an exponential, and we do know how that goes. So the result is a fraction with s as the denominator and the exponential of minus as as numerator, a being the shift in the Heaviside function. Let's go to the next step. Let's look at what we called the translation function with respect to the Laplace transformation. So we know that we want to calculate the Laplace transform of a function times an exponential. And what we notice by just applying the Laplace transform to that is that if we have the exponential of at, that can just bulge up with the exponential of minus st that we have given by the integration kernel of the Laplace transform. So as a result, what we have is that the Laplace transform of e at the it times f of t is the Laplace transform of ft, but calculated instead of at s minus a. This is why we call it the translation function. It's translating the Laplace transform of a function by a value a. So as a new element, let's look at the Laplace transform of a translation times the Heaviside function. So we have the Heaviside function calculated at t minus a, and f that is also computed at t minus a. So if we take the Laplace transform of that, we have an integral with our Heaviside t minus a, f t minus a, exponential minus st. And what we're going to be doing is we're going to define t minus a to be tau. So dt is equal to d tau, and we can have this change of variables. And here there is a typo. All the t's should be taus now. But now our Heaviside function and our f have been shifted to be computed at tau. And our integral is now going from minus a to plus infinity. But the Heaviside function is 0 before 0. So we can just cancel that out and have just a multiplication of the Laplace transform of f by the exponential of minus sa. I will also introduce the Laplace transform of derivatives. We have seen how the first derivative goes. It's actually a recursive formula. So the Laplace transform of the nth derivative of f is sum of terms in which the first term is the Laplace of f times s to the power n, and then we subtract f computed at 0 times s at the minus 1, and then we shift the powers of s, we decrease the powers of f s, and we increase the derivatives of f. So we go from Sn minus 1 f0, Sn minus 1 minus 2 f prime, to s to the power 0 f n minus 1th derivative of f. All of those calculated at 0. You had it as a homework to prove it, so I'm not going to go through it. I expect you to have understood it by now. If you have any question, obviously ask.